Welcome to today's video where we're going to be going from this circuit board to this one, which clearly on this one, I got the footprint wrong if you haven't seen the video already. So yeah, this one, I already did a video on it where you got the footprint wrong. This new one, I got the footprint corrected, so we'll get this thing put together, verify that it's correct, and we'll take a look at some of the code and stuff in this video today too. Okay guys, let's talk about today's sponsor, JLC PCB, who sent us our PCBs for today's project. Today we're actually going to talk about their SMT assembly service because not everybody knows they do it, and it's a good deal. It starts at $7 and it has a 24-hour turnaround, so super fast. My personal recommendation, if you are going to use their SMT assembly service, is to use Easy EDA with it, so that way you know what they have in stock and all that. It ties it all in. So if it's possible, use Easy EDA. Now, it's not required to do that. You can design in your own CAD software and they can still do the assembly service. So some of the things to keep in mind is if you need hand soldering, so if there's like through-hole components, that does add a $3.50 charge in 1 day on the assembly, but that's still an amazing deal for what's going on there. You also can do BGAs with this. Not everybody supports BGAs, but JLC PCB does. All right, so let's do a little bit of assembly work here. May take me a little bit dialing in. I'm trying a different tip out here, but yeah, we're just gonna go and give this a shot. Trying a different angle here too. But yeah, let's get right to it. All right, so now let's go ahead and burn our Intel hex file onto our Atmega 328 here. So what we're gonna have to do is first export it out of Arduino. So you go into Arduino, you go to Sketch, and you do export compiled bin. Now, the way this PCB is laid out, you could actually use the upload using programmer and use an Arduino as an circuit programmer, but I'm gonna use the Mini Pro because I have the chip socketed and it's not even in the socket yet. If I were to be writing it a lot of times over and over again, these cheap sockets like this will wear out, so I would just do it in circuit. But this time, I'm not gonna be doing it in circuit. So you just export your compiled bin, which I've already done, and then you load it up into Mini Pro. Just make sure you have your Atmega 328 selected as your IC, and then you're going to go to Config, and in your config, just make sure you have your high fuse set and your extended fuse set. The rest are all blank. So just make sure these two are set. And also make sure you don't accidentally load your Intel hex file in as a config file. It messes everything up and you have to exit out of Mini Pro. It won't let you set the stuff right. I did that by mistake earlier. So yeah, once you've done that, you can go ahead and program it. So let's program. And there we go. We have successfully programmed our Intel hex file onto there. So now let's drop it in the socket and see if it works. And there we go. It is working. So, all right. So I'm going to cheat a little bit on this CAD work here. There's just no way I'm going to do it with this light in my face and make like a 2-hour video of me fumbling through CAD. So I've actually already made it and we're just going to play through the design here. So first thing we got to do is just create our initial sketch of the footprint of the whole part here. Then we extrude that up 2 millimeters. We make our initial sketch of the footprint that's going to be holding the actual cards in it, which was like 15 millimeters. Go ahead and extrude that all the way up to height. Now we make our sketch of the triangular shape of it from there and extrude that out, because I like just doing extrusions for everything. It's all I really know how to do in CAD. All right, so now we do a shape up top there for the cards themselves to go into, basically giving us 2 millimeter of wall on each side there. Go ahead and extrude that down. I forgot how far I went down there, but it's not necessarily that important. That's just far enough. I think I just kind of guessed. There was no rhyme or reason to it. I just like took a card and was like, this is about halfway down the card. All right, so then I put a nice little fillet around it. And now we're going to do a sketch. This is of the size of the card itself, plus 1 millimeter on each side there. Go ahead and extrude that down. I extruded it down 4 millimeters because we're going to do 2 millimeters of standoffs. So now we do our sketch of our actual standoffs here and extrude them up. I extruded them up 2 millimeters because the PCB itself is about 2 millimeters. So that's going to put the PCB sitting nice and flush with the surface here. And then we have to put our screw holes in it. So do a sketch for all of the screw holes and extrude them down one at a time. And I just extruded all of the screw holes down 10 millimeters, which actually comes all the way through right there. So next we put some fillets on the standoffs, just so that way they're nice and smooth, no high points on them. And then just for a little extra rigidity there with the 3D printer, also put a fillet there that makes it kind of stand off a little bit more there. So that is all we had to do for our CAD work there. It's pretty simple. So then we just go to the body, right click body and save as mesh, and then just save it as an STL and open that up in Cura so that way we can do it. So here it is in Cura. Already got it laid out here. We do need supports on this. We only need 20% infill. Don't pay attention to my other specs. I really don't. I'm not an expert at 3D printing here. I just wanted it to go a little bit faster. Let's see here. And yeah, we need supports everywhere. The only places it's going to generate supports are right here. So we can go ahead and go to preview and you'll see the supports. There you go. You can see where it did supports right there, and that's it. So now let's go ahead and save this and get it running on the Ender 3 and start printing it. All right, so just about 9 hours later, and we now have our 3D print. All we have to do here now is just take off these supports, but other than that, came out pretty clean. And it's a nice cold day, so came out to the office and it came right off this glass top. That's what I love about the glass tops for the 3D printers, is as long as you let everything cool down again afterwards, it comes right off. There's no popping, peeling, or, you know, having to get the scraper out. They can be hard to get off when it's still hot though, but if you let it cool down, this PETG comes right off of it. Okay, so let's get this thing assembled. It's just 3 screws, so nothing too crazy here. Just drop it in there, and it is I'm using a M2 8mm screw. I think 8mm is about as long as you'd be able to get away with. It really probably should be a 2M6 instead. A little bit shorter, so that way you're less likely to poke all the way through back here in the back. I'm just barely not poking all the way through, but in measurements of everything, it should poke through just a little bit. I don't know if it's the 3D printer printed it just a little bit fatter than it really should be, or if these screws are just a little bit shorter than they are actually supposed to be. So, but yeah, it should be poking out the back here, but it's not. So yeah, I don't know. But let's go ahead and plug it in now that we got it assembled and everything fits nicely. And there you go, it is working. And that's not actually flashing in person, that's just the refresh rate of the camera with the refresh rate that I used on here. So camera picks up a little bit of flicker, but in real life, you don't see any flicker here. Business cards will fit in there just like that. So you have your business card sitting in there and it'll attract your customers there. They'll see, oh, that's kind of neat. Oh, look, a business card, let me take one. If you want to build this project, all of the files will be on my GitHub, so you don't have to buy anything from me. It'll all be right there on the GitHub. You can download it all. The BOM for assembling the circuit board files, so that way you can take it to a board house. I'd recommend JLC PCB. They sponsored the video, so you should check them out for it. But you can take them to whatever board house and they will work there. And yeah, so you'll have the Arduino sketch in there. So I'm going to upload it as a sketch, and then you can go into Arduino and turn it into a bin and program it. That way, if you want to make any changes to the code, I'll also upload the schematic to it and the footprint that I made in KiCad for the screen here. So that way, if you want to use this in a different project, if you wanted to actually make like a functional park reverse neutral screen that runs off of, say, CAN bus or something, you absolutely could do that. The files are there for you. So that's what I'm going to upload into GitHub. So you'll have pretty much everything. So check out the GitHub. There'll be a little written description of how to put it together too. I'll have these 3D print files on there. So I'll just have the STL up there. If there's any demand for the Fusion 360 files, I'll put them up there too, but I don't see why anyone would need it. As for what do I have left over? So I have 3 blank PCBs. If anyone just wants a blank PCB, I do have 3 of them. If anyone wants a fully assembled one, I have one that's already fully assembled, but I also have all the parts to fully assemble I think I have enough to do all 3 of them. I might be short 1 microcontroller. Okay, so real quick before we end the video, I just want to explain a little bit of the Arduino code, so that way for anyone that pulls this out of GitHub and wants to do something with it, they got a little bit more understanding of what's going on here, because I definitely didn't follow best practices writing this. So you got your typical defining of what pins are and what the pins do, but then you come up to this first void and it's labeled void screen. It really would be more accurate to label it MIC 5891, which is that serial latch that's there. So all what we're doing in this function here is we're shifting in each bit one at a time. So basically we get this value, which the value is here, and we're going to shift it in each byte. So we're going to use the read byte function to do it. So, or sorry, read bit. So we're going to do it 1 bit at a time. So we know that it's going to be 8 bits. So we need to for loop it for 8 bits, and just read byte 1 at a time, send in the clock. So what we're doing is select low, and then we're going to read our data bit, so it's either a 1 or a 0, shift that in, and then we're going to give it clock, and then we're going to repeat until we've finished this this section. So obviously this stays low, it's outside of the for loop for the whole time, so that's the for loop, and then once it's done, you just the select goes back high. And that is all there is to that function here. This poll button function is just, it was that way I could make this button functional. So really it's just like, hey, is the button high? Okay, let's do that if it is. Didn't debounce it because of the way it's going in here. It really doesn't pull it that often. So every 7 milliseconds it gets polled again, and while it's running there's a delay in it, so it won't do anything for another 650 milliseconds. So yeah, it doesn't get pulled that often, and there's a delay in it, so there was no need to debounce it. Like, this delay itself is debouncing the button. If I were to change what the button was doing and stuff, yeah, I would need to debounce it, but just because of what's going on there, no debounce written in. So then we just have our loop void, and we're just gonna set a timer and use the timer, and basically while the timer's running we shift in between. So C2 would be okay, C2 is the the PRND and the the PRN and the D321 lit up. So those are two separate grids, but we're lighting up both of them at the same time. So that's what's going on with the C2, and you'll see the C2 over and over again. And then 90, that one is the underline for the P. So that's how that works. So, you know, we shift this in, and we're going to shift this a lot. See, we're 7 millisecond delays there, so we're pretty much constantly shifting data into our register there. Well, it's not really a register; it's a serial latch. But yeah, we just keep putting that data into it to tell the screen what to do. I probably could have gotten away with using like a level shifter instead and just gone direct from the microcontroller, writing the pins high and low to do stuff, but I don't know. I wanted to pretty much copy what GM was doing in theirs, because this is exactly how everything in here is exactly how the GM park reverse neutral screen works on here. We have the exact same circuit for the filaments. Obviously not the same power regulation in there though. I am regulating the power differently. Obviously this is not the same serial latch that they used. The one that they used is no longer produced. I wanted to use something that was off the shelf, and obviously this is a different microcontroller. But regardless, this works exactly the same, just the pin layout's different. So it is still doing, yes, it's a different chip, but no, it functions the same. So it's doing the same thing. And that's what I wanted to do. I wanted to make it the same, so that way people get a better understanding of what's going on in the GM instrument clusters that work on the clusters. But also, I just wanted to do it for fun. All right, I hope you guys enjoyed the video. I know for my regular subscribers, I mentioned that I was going to show how to do the footprint in KiCad for this, and I am going to show that eventually. It's just, we're already at 20 minutes in this video, so there's no point in doing that in this video. We can separate that out. I can probably just do a YouTube short on how to make the footprint pretty quickly. I just didn't want to put way too much in this. I already have 3D printing, CAD, assembly, and Arduino, and programming all in this video. So yeah, adding the KiCad would have been just one more unnecessary step in this video. Like I said before, it's going to be on GitHub, so you can download it all. You can go to our sponsor for today's video, JLC PCB, and you can order the blank PCBs from them. So for anybody watching this video that wants to build one of these themselves, and they don't know where to find this particular screen in it, you can find it in a 2003 to 2005 GM instrument cluster, and you can also find the that same screen in quite a few of the Trailblazer instrument clusters. So I'm not sure on the years of those off the top of my head, but it's the same screen in both of them. If you get it out of the GM trucks like the Silverados and Suburbans and all that, you can also grab this row of resistors right here off of it, because I used that same thing. You could also salvage the button off of the instrument cluster too if you wanted to. Other than that, then you'll have to order the rest of these parts. So that's Yeah, I copied the design of that just to make an example of how to use the screen, since there's not a data sheet available for it either. You can't get the data sheet to the screen, but these are nice looking vacuum fluorescent displays, and eventually I'll probably do a CAN bus project with it where you can incorporate these into your LS swaps or whatever. So I hope you guys enjoyed the video. If you haven't already, please subscribe to the channel, and I'll see you guys in the next one.